82. You have to look at the other side to guide you on what you need to do. And what I mean by that is, let me write it out real quick. So we have 1 minus sine squared x times 1 plus sine squared x equals 2 cosine squared x minus cosine to the fourth x. Okay. So your natural instinct might be to distribute this. You have to fight your natural instincts on that. Because you first have to look to the other side. See how the other side has no sines in it? It's all cosines. And the left-hand side is all sines. You need to change everything on either the left-hand side to be all cosines, or you need to change everything on the right-hand side to be sines. So I'm going to focus on that left-hand side. Because starting it off isn't so bad, because if you remember that we have sine squared plus cosine squared equals 1, we could see that cosine squared equals 1 minus sine squared. What? So I could take that first part that's 1 minus sine squared and change that to a cosine squared. You guys gonna be okay? You sure? Okay, so we have just cosine squared. Well, I need to change this sine squared. Currently, it's 1 plus sine squared. 1 minus, that doesn't work. That doesn't work. 1 plus sine squared does not work with this. So you have to think of another method. So what I'm going to do here is I'm going to rewrite that sine squared plus cosine squared as 1 as just sine squared equals 1 minus cosine squared. Why that's important is because anytime you have just sine squared, you can then replace it with 1 minus cosine squared. So what I'm going to do is I'm going to take that 1 minus cosine squared and I'm going to throw it in place of just that sine squared. So rewriting that, so we have cosine squared times the quantity 1. I didn't do anything with that 1. I'm just adjusting that. Plus, and in the place of sine squared, we're going to replace that with 1 minus cosine squared x. Now we'll just do some math. I have cosine squared x. 1 plus 1 is 2 minus cosine squared x. And when I distribute this cosine squared to both these things, we're going to have 2 cosine squared x minus cosine to the fourth x, which is what I had on the other side. Oh, okay. All right, other questions? Mary? Hope? Did I call you Mary last time too? Yeah. You guys are just in my peripheral. No, they're Mary right there. When I'm looking at it, I just, yeah, Hope. 79. I'm going to move you guys further apart, I think. All right, 79. 79 is, 79 you have to factor the top. So factor the top. So what I'm picturing on 79. So on 79 we currently have sine squared plus sine minus 2 right on top there. What I'm actually picturing is x squared plus x minus 2 on top. Because sometimes picturing it as x's can make it easier to factor. Factoring that, we would have x, a binomial. We have x up front to give us our x squared. To give us our 2, I need a 2 and a 1. We have a positive middle term, so it's a positive 1 and a minus 1. So replacing those x values with back to our sine of beta, you should have on top sine beta plus 2 times sine beta minus 1 all over 2 sine beta minus 1. So on the denominator, I did factor out a 2 as well.
Oh, okay.
And then these cancel out. And is that what the other side is?
Yeah.
Okay.
Okay. Thanks.
Is that enough? Or do you need more? We're good? Something felt very off today in the back area. And it was like a seating that I did not make, and I know I didn't make it. I just couldn't figure out what it is, but I knew people weren't in the right spots. All right. Yeah, so we're going to walk through them. Sure. All right, so on this one, we have cosecant. This is probably the last one we can go through. The rest I'll have to just take pictures of because we're running out of time. Over cosecant y minus 1, and that's going to equal 1 plus sine y over 1 minus sine y. I'm going to do it different than how I did in the answer key. It'll be the exact same method, but on the other side. All right, it's like that cosine and sine one that we had before. We're going to notice I have nothing but cosecants on this side and sines on this side. So I need to either write the left-hand side in terms of sines, or I need to write the right-hand side in terms of cosecants. So on the answer guide, I wrote these as cosecants. This time I'm going to write these in terms of sine. So that's going to give me 1 over sine y plus 1. Let me build that wall up. And that'll be all over 1 over sine y minus 1. So I'm just changing cosecant to sine. Now I have fractions in my numerator, I have fractions in my denominator, I want to get rid of them. The easiest way to get rid of a fraction is to multiply by its denominator. But you have to make sure, so on the bottom one I have to multiply by sine y, which means I have to multiply the top by sine of y, and it just so happens that that's exactly what I wanted to have happen on the top. Because now I distribute that sign there, I would distribute that sign there. So in our numerator, you have sine over sine, which is just 1, plus sine y times 1 is sine y. In the denominator, we distribute it like that. And we're just going to have sine over sine, which is 1, minus sine times 1, which is just sine y, which is exactly what's on this side. But that is the exact same process I did on the answer guide. I just did this with cosecant on this side of my answer guide. All right, other questions? Yeah? 83. Specific questions or just? I'll just go through it.
Yeah.
I don't have a great, this is not going to take a great picture, but anyway. All right. Clear that. Take the old pictura. All right, this is another example of one that I let the other side. So I'm going to work on the left-hand side. It's slightly more complicated because we're adding. And what I'm going to look at is the other side is secant and cosecant. Secant and cosecant tell me cosine and sine, because I can always change things in terms of sine and cosine. So I'm going to change tangent to cosine and sine, which would be sine over cosine. And then I'm going to change cotangent to cosine over sine. Now, I have two fractions here, and on the right-hand side I just have one thing. I don't have any addition or subtraction. So what we need to do is we need to push these two things together. And the only way to do that is to have a common denominator. To do that, we're going to multiply one fraction by the other's denominator. So I'm going to multiply that left-hand fraction by sine x over sine x. And I'll multiply the right-hand fraction by cosine x over cosine x.
You can multiply them by different things.
So I'm multiplying by 1. Sine over sine is just multiplying by 1.
They're both just times 1.
They're both times 1, yeah. So I can do whatever I want. I can do 16 billion over 16 billion.
Yeah.
It's not going to help you here, but you're allowed to do that.
So I was just confused. I went from sine over cosine plus cosine over sine to the
To this?
sine squared over sine. Yeah.
This is all I did. I just multiplied by the other.
Multiplied or something, but I didn't think
It's not cross multiplying.
Yeah.
Cross multiplying only works if
Yeah,
you have
I
an
didn't think you
equal.
could there, so
Yep. Nope, you just multiply by the denominator on top and bottom on both. And that's how you get that. When you push it together, you get sine squared plus cosine squared, which is 1, which is actually the end.
And also, for question 85.
Mm-hmm.
I thought there should have been a negative somewhere.
I dropped the negative somewhere.
No, I didn't. Well, I didn't know why it didn't.
Oh, why I didn't have a negative?
Yeah.
I'm not sure where. Let me take a picture of that.
Yeah.
So this is almost the exact example as the one to the left. In the fact that I had to push these together by multiplying by the denominator. So I multiplied this one by secant over secant, and I multiplied this one by tangent over tangent. That's where I got that from. When I condense it, secant squared minus tangent squared is a positive 1.
Maybe that's right.
It is actually a positive 1. It's not a negative 1, the way it works.
All right.
Okay? Other questions? Yes, now or forever hold your peas and carrots. That's exactly how it goes. Okay, so let me just go over what's going to happen this week. Today we're learning something new.
Yay.
Tomorrow we're going to just practice on identities that we have. I'll just throw more identities at you because the more practice you have, the better you get at them. Also, we don't have a homework. It's a no homework weekend.
Yay.
So basically, however many you get through, it's a good thing. A little incentive to it. One of the ones that you work on tomorrow will be on the test, or one almost exactly the same. So it's good incentive to actually work through them as practice and not just go, oh, it's not homework, I don't have to do it, kind of thing. All right, so tomorrow's going to be mostly just a work day. Yes, Mary. I do, and so do you.
30th.
Oh, right. Sorry.
30th, yeah.
My bad.
He read my mind.
So this homework we're getting tonight is due Tuesday.
It's due tomorrow.
So the test is on the Tuesday?
I am Tuesday.
No. Wednesday's home. Tomorrow we're doing verifying it.
No, it's not.
Just pretend like I didn't say anything. We'll just,
Like homework or no homework?
it's no homework weekend.
Oh, okay. So you can't give homework?
I can't give you homework.
No.
And I won't check for homework on Tuesday. Okay.
When's the test?
Anywho, all right, let's get to the sum and difference thing. Because I don't care if I don't get through it, you can watch the other video. All right, so we're doing a sum and difference identity. Now, when we use our units, I really got to put my unit circle back up there. We had very key values we could look at. We could look at pi over 4. We could look at pi over 6. We could look at pi over 3, pi over 2, so on and so forth. However, there's tons of measures out there. In fact, there's an infinite number of measures that aren't on our unit circle. Well, we're about to expand our horizons on ones we can actually use the unit circle on. So, for example, if you look at a unit circle, 75 degrees is not on your unit circle. However, what is on your unit circle is 30 degrees. What is on your unit circle is 45 degrees. And 30 degrees plus 45 equals 75 degrees. However, you can't just get your sine value at 30 degrees and your sine value at 45 degrees and add those two values together. It just does not work that easily. And in fact, we have to, when we are adding two angles to get to one, we have to use one of these identities. Yes. You do have to have those memorized. And correct me if I'm wrong. I think yours is correct. Does yours have a plus or minus here? Minus. Okay. I'm just double checking because mine did not. So that should be a minus. That should be a minus.
Memorize all of those or just a tangent?
Yes.
I only picked one.
And that should be a plus down there. Only pick one to memorize, and hope I put that one on the test. Unfortunately, if I don't put that one on the test, you're kind of done. So, all right. You should have a very good idea of these. That is my hint on the test. So you should have these pretty much memorized. They aren't that bad if you catch the flow of them. Sine of A plus B is sine A cosine B. plus cosine A sine B. So in fact, you just have to find your sine and cosine of both of them and add it to the sine and cosine of the other one. The order doesn't necessarily matter. When you subtract, you just throw a subtraction sign between the exact same thing. For cosine, both your equations are the exact same, except when I'm adding the angles, I subtract on the other side. When I'm subtracting the angles, I add on the other side. Tangent is probably the toughest one, but the good thing about tangent is it just has tangent values. Is tangent of your first plus tangent of your second all over 1 minus tangent A times tangent B. If you're subtracting, you just have subtraction on top and addition on the bottom. All right? No easy way to split it. You just have to know these. All right? Which turns into just memorization. Yes?
Our sheet for the second tangent has a minus.
On the bottom? It should be a plus. Something happened there. I'm not sure.
Wait, what?
On the second, on the right, change the bottom one to
Yeah.
addition.
The correct ones are right below it. If you look right below it,
This should be 1 plus 2.
it should be 1 plus tangent alpha, tangent beta. Yep.
Is the left one right?
Yes, the left one is right. And these two are 100% right.
It's in the rise also.
Those are the same ones. I just re-put them so it can make these problems a little easier. So you don't have to turn the page. Look on the next ones. Okay, guys. We can't keep getting off on these tangents. Knee slapper. Knee slapper. And speaking of tangents, we have to find the tangent value of 7 pi over 12, which your unit circle does not have on. So when we're dealing with radians, what a good idea is pick radian values that you know are on the unit circle. So I'm going to put a little notes to myself off to the right-hand side on the top corner. I'm going to say, I know pi over 6. I can find tangent values of pi over 4. I can find the tangent value of pi over 3. I can find the tangent value of pi over 2. And if you want to, you could keep listing, but all we really need is in that list. Now, my goal is to add or subtract 2 of these angles to equal 7 pi over 12. However, to see that, it'd probably be a good idea if they already had that denominator of 12. So I'm going to rewrite pi over 6 as 2 pi over 12. I'm going to rewrite pi over 4 as 3 pi over 12. I'm going to rewrite pi over 3 as 4 pi over 12. And I probably could stop there, but just for fun of it, we're going to have 6 pi over 12. What 2 angles can I add together that would equal 7 pi over 12? Mary. Pi over 4 plus pi over 3 would equal 7 pi over 12. In other words, we're looking at right here, which you could put as, because since 3 pi over 12 plus 4 pi over 12 equals 7 pi over 12, that would mean that pi over 4 plus pi over 3 would also equal 7 pi. This one's the more useful because 3 pi over 12 is our unit circle, but I don't want to have to keep transferring it in and out of it. So this is our key one right here. We are now going to rewrite that 7 pi over 12. So we're going to say in this next step that, tangent of 7 pi over 12 can be rewritten as tangent of 4 pi over 12 plus, not over 12. Let's go back. Go back in time. I wanted to use the other versions. I want to use the pi over 4 plus the pi over 3. It just makes our life a lot easier if we don't go down the other rabbit hole. I didn't do anything. It's all algebra. That is algebra, breaking apart a fraction. Right? If I have 4, I can rewrite it as 2 plus 2 or 1 plus 3. That's all we're doing is rewriting this. Now it fits in this box here because I have alpha plus beta. Your alpha is always going to be your first, and your beta is always going to be that second value there. So now we're going to plug it into that identity. The identity says, well, tangent of the first angle plus tangent of the second angle. So we're going to have tangent of the first angle, which is pi over 4, plus tangent of the second angle, which is pi over 3. All over, if I have plus on top, I'll use minus on bottom. And that'll be tangent alpha times tangent beta. So it'll be tangent of our first angle, pi over 4, times tangent of my second angle, which is pi over 3. Yes?
So it doesn't matter which one's alpha or beta for this?
It does.
Like, how do you know?
Alpha should be the first one. Beta should be your second one.
Well, like, what if I thought pi over 3 was the first one? Like, how do you know?
Oh, in this case,
Yeah.
it's not so important until there's a subtraction sign.
But, like, how do you know which one's first or second?
You're going to know when you subtract and it either becomes a negative or the angle you want it to be. We'll have a subtraction on the next one. Because picture this. 4 pi over 12 minus 3 pi over 12 is pi over 12. If I'd accidentally flip it, I'd have 3 pi minus 4 pi, which would be a negative pi over 12. You'd put it in the wrong order. Addition, it really doesn't matter, because like you said, this could be pi over 3 or pi over 4. Doesn't matter. With addition, it doesn't matter at all. It only matters when we're doing subtraction. So that's a good thing to recognize. All right. Well, all this is on our unit circle. Tangent of pi over 4 is actually the easiest tangent value, because it's where pi over 4 is where sine and cosine are the same value. They're both square root of 2 over 2. So that means our tangent of pi over 4 is just 1. Plus, who can give me the tangent value of pi over 3? You should have a 50-50 shot at getting it. Yes?
Radical 3.
Yes, it is. It is radical 3. And now that we know both those values, we can go to the bottom. We say 1 minus tangent of pi over 4 is just 1 times radical 3. I'm going to get some of this stuff out of my way real quick. Are we allowed to have a radical in the denominator?
No.
On the test, you're pretty good right here. You'll get almost all your points. Because this... I don't want to know. All right. To get rid of a radical is super easy if it's just alone. If this was just square root of 3, I'd multiply the top and bottom by radical 3 and we'd be done. This is not the case. Yeah?
Don't you take the reciprocal or not the
Conjugate. Yep. We have to take the conjugate. And the conjugate of our denominator is 1 plus square root of 3. So we're going to multiply our denominator by 1 plus square root of 3, but I'm not allowed to just do it in the bottom. It has to happen on top. And we'll have something like that. So that is the conjugate. Well, these are two quantities being multiplied. So I have a binomial times a binomial on top, and I have a binomial times a binomial on the bottom. So tackling that top, I don't care how you distribute it. How I usually distribute is I take that first term and I multiply it to both things to give me 1 plus square root of 3. Then I take the next one, which is the square root of 3, and multiply it by both of them as well, which would be square root of 3 times 1, which gives me another square root of 3. And square root of 3 times square root of 3 is just 3. You have to know that. Some people struggle on that. If you struggle with it, come see me. You have to just know that fact. And that's going to be all over a minus b times a plus b. So I have 1 minus square root of 3 times 1 plus square root of 3 is a squared, which should be 1 squared, or just 1, minus my b squared. Square root of 3 squared is just 3, which is going to simplify down to 4 plus I have 2 square root of 3's, all over a negative 2. Keep going. We can split this apart into two fractions. 4 over negative 2 plus 2 square root of 3 over negative 2, which reduces down to negative 2 minus square root of 3. But realistically, if that looks like a daunting task, this is where most of your points are. All right, before it's simplified, you get most of your points. Yes?
I got it wrong. Well, instead of just like splitting it apart, I like factored out a 2 as denominator and then canceled the.
And you come with the same answer, right?
No, I got -2 plus square root of 3.
-2 plus. Well, you would have pulled out a 2. So here's what happened. So you pulled out a 2 out front, right? Which would have turned this into parentheses.
Right.
That negative down here would have transferred to both things in the parentheses. Real quick, no one pay attention to this unless you did this. Yeah, close your eyes. Close. So you factor out a 2. Right? And then you canceled this out.
Yeah.
That negative would distribute to both elements of your thing.
Oh. Okay.
All right, everyone can open your eyes again. All right, we're good. All right, let's move on. So we don't run out of time. All right, our next one is expressing cosine pi over 12 exactly, which means I have to use the unit circle. Pi over 12 is not on our unit circle. So once again, you pick some major angles that you know of. Let's pick pi over 6, pi over 4, pi over 3. One of those should suffice. If not, you just keep finding new ones like pi over 2. Well, rewriting pi over 6 with the denominator of 12, we're going to have 2 pi over 12. Then we'll have 3 pi over 12. And pi over 3, you have to multiply top and bottom by 4, which would be 4 pi over 12. All right. There isn't just one correct way to do this. There isn't just one correct way to do this. So can someone pick one of these using adding or subtraction that would actually work? Emma.
Pi over 3 minus pi over 4.
Pi over 3 minus pi over 4. Do we also see how pi over 4 minus pi over 6 would also work? Both of them will come with the exact same answer. All right, we're going to do the pi over 3 minus pi over 4 because that's what Emma said we had to do. So we're using those values, and we have to use pi over 3 minus pi over 4. Nicholas, do you see how you know which order it has to go in? If you flipped it, you came up with the wrong angle. So this has to be my alpha. This has to be my beta. It has to be. So we are going to rewrite this as cosine of, instead of pi over 12, we're going to convert it to, well, basically we're doing 4 pi over 12 minus 3 pi over 12, but we're going to write it as pi over 3 minus pi over 4. Cuckoo, ka-choo. All right, so we have a subtraction. So we have to use this one, yeah. Because it's just our first. See how this is alpha? And they just match up? So you're always going to call your first one. The first thing here are alpha, and the second one's always going to be your beta.
Yeah.
Just so you know where you're plugging it in here.
No, yeah, I see it now.
All right, so I have a negative sign. I'm subtracting angles. So we're actually using an addition sign. That's where it gets a little confusing with cosine. So we're going to do cosine of one of the angles times cosine of the other angle plus sine of the angle times sine of the other angle. So cosine of our first angle, which is pi over 3, times cosine of our second angle, which is pi over 4. We are going to add sine of the first angle, which is pi over 3, times sine of the second angle, which is pi over 4. All of these values are on a unit circle. I'm just going to kind of fire through them. So pi over 3 is our third tick mark. We have pi over 6, pi over 4, pi over 3. Cosine of pi over 3 is 1/2. Times cosine of pi over 4 is square root of 2 over 2. Plus sine of pi over 3. Well, if cosine is 1/2, that means sine must be square root of 3 over 2. And sine of pi over 4 is 1/2. That's going to equal 1 times square root of 2 is square root of 2. 2 times 2 is 4. Plus square root of 2 times 1 is square root of 3. 2 times 2 is 4. The most we can do is push the fraction together to be square root of 2 plus square root of 3 all over 4. Can't simplify it any further because I can't split it apart in fractions that reduce. Bree.
Is it sine of pi over 4 square root of 2 over 2 and not 1 half?
It should be square root of 2 over 2. You are 100% right. That's what happens whenever I hurry up. Thank you. I said it. I just didn't write it. But that doesn't change too much. It just changes this to a 6. And now we have square root of 2 plus square root of 6 over 4. Thank you. Now we're good. All right, we're going to do the exact same thing for our next one. The good thing about the next one, I think it's a lot easier when it's in degrees. It's a lot easier when it's in degrees because we don't have to do any converting. We just got to pick our major degrees. And I'll hold on for 1 second while people still write. All right, our next one's in degrees. So we just have to look at our major degrees that we have. We have 30 degrees, 45, 60 and 90 are basically our first few major ones. So once again, you're just thinking, well, we have a 30 degree, 45 degree, and a 60 degree. And once again, you have multiple methods. You could do 60 minus 45. You could do 45 minus 30. Both of those will work out the same. Let's just do 45 minus 30. So we're going to rewrite this as sine of 45 degrees minus 30 degrees, because 45 minus 30 does equal my 15 degrees. Well, we are subtracting, so we'll use the subtraction one, which is sine of our first angle, which is 45, times cosine of our second angle, which is 30, minus cosine of 45 times sine of 30. So let's go ahead and write that. So we're going to have sine of our first angle, 45 degrees, times cosine of my second angle, which is 30 degrees. With sine, if I'm subtracting angles, it is a subtraction sign. So we're going to have minus cosine of the first angle, which is 45 degrees, times sine of the second angle, which is 30 degrees. All these values are on a unit circle. Sine of 45 degrees is square root of 2 over 2. Cosine of 30 degrees is square root of 3 over 2. Minus cosine of 45 degrees is square root of 2 over 2. And sine of 30 degrees is 1/2. Bree, did I get all those right this time? Mm-hmm. Awesome. All right, so we have square root of 6 over 4 minus square root of 2 over 4, which only simplifies down to pushing the fractions together. So square root of 6 minus square root of 2 all over the big 4. Honestly, the only complicated part about these is just memorizing the formulas. Otherwise, it's just plug and chug. Figure out what fractions add together to give you the fraction that was given to you or the degrees that were given to you, and then it's just plug and chug your way through it as long as you know your unit circle. All right, the very last thing we're going to talk about are called cofunction identities. Cofunction identities. A trig function of an angle is equivalent to the cofunction of the complement of the angle. All that's saying is, you know how all your values repeat themselves? Like sine and cosine can only be one of three things. They can either be 1/2 square root of 2 over 2 or square root of 3 over 2. So because of that repeating factor, you could say something like this. Sine of pi over 2 minus some angle. So say you have sine of pi over 2 minus, 3 pi over 2. That's going to be the exact same thing as cosine of 3 pi over 2. If you have cosecant of pi over 2 minus, 2 pi over 3, that would equal secant of 2 pi over 3. If you have the tangent of pi over 2 minus, say, 6, that would equal the cotangent of just 6. These can be useful if you need to transfer between two different, like sine to cosine. So our example here is use a cofunction identity to find the exact value of sine of 5 pi over 12. Well, we're going to use the cofunction identity where sine of an angle, u, is going to equal cosine of pi over 2 minus u. Well, we were given sine of 5 pi over 12. So that means I'm replacing u with 5 pi over 12. So we're going to replace it here too. So cosine of 5 pi over 12 is going to be equal to cosine of 5 pi over 2 minus, pi over 2 minus 5 pi over 12. Well, that's going to be cosine of, instead of pi over 2, we're going to go with 6 pi over 12 minus 5 pi over 12, which is going to equal cosine of pi over 12. We did cosine of pi over 12. Yeah.
Is it square root of 2 plus square root of 6?
All over 4, right? Yep, because we just did that. We just did that. Square root of 2 plus square root of 6 all over 4. So that's going to equal square root of 2 plus square root of 6 all over 4. If I was you and these were my notes, I'd put a little note that says something like from example 2. Because if you're anything like me, you study your notes for your finals, and all of a sudden you're like, where did I get that number from?
What's the point of this?
So we could transfer between things and use the unit circle to come up with exact values. So like this one, I didn't.
What's the point of I don't know, changing it from cosine of pi over 12 to the other one? How is that less complicated?
Well, we already know cosine of pi over 12.
Yeah, I know.
This is so much easier than me actually forcing you to go, well, find sine of 5 pi over 12, and you have to do all those steps. I find this a lot easier because I can do a lot of it in my head versus all of that. And you can bet that when we're doing this, we're picking a method that makes it easier for you to find it on a unit circle. All right, so we're just showing two methods of how to find things on a unit circle that might not be on the unit circle. So on the test, if I say find the exact value, you could think of two different ways to figure it out.
So we can do it either way?
You can do either way. However, this is the main way. All right, that's why we only had one example of this. This is not used very often. Yeah.
Would you be required to do it when you're or
Would you be required to if I say use cofunctions? So I would think the only time you're going to use this is if I tell you to. All right, because I have to make very strict parameters that it actually works.
Oh, yeah.
Otherwise, you're going to spend a whole bunch of time doing this and find out that it's not helping you. You have to go back to the original one. Bree?
For the test, we have to do the unit circle again, or are you gonna give it to us?
You should know the unit circle.
Well, yeah, we know, but
You know, but...
it's still like a lot of memorizing with all that other stuff too.
You're making points. I don't disagree.